So, welcome to the 25th session of the second module in the course Signals and Systems. And here we carry our journey further to seek an inverse for the Fourier transform. Let us see where we are, just to get our bearings right. What we have seen is that if I try to calculate this integral minus infinity to plus infinity h omega e raised to the power j omega t d omega multiplied by a constant kappa 0, essentially taking vector intuition that you multiply components by unit vectors along those components and integrate over all the components. This can be rewritten as summation minus to plus infinity kappa 0, and we have another integral inside. I am just reviewing this because this is a little involved, there is no harm in repeating this a little bit. I will write here, it is a recap, we need to do a recap, and then we rearrange this. We said you could keep ht1 outside and then take the omega integral inside, and kappa 0 being a constant we could keep that outside, and then look at the integral e raised to the power j omega t minus t1 d omega, and this is then integrated with respect to t1, and we were trying to evaluate this integral, and let us look at it once again. This was essentially kappa 0 minus to plus infinity e raised to the power j omega t minus t1 d omega, and this could be written again as twice kappa 0 times t1. We said we must take this as a limit. So, we said we could think of this as kappa 0 limit, and this time let me try and improve my notation. So, I will say limit as omega 1 tends to infinity. I will improve my notation minus omega 1 to plus omega 1, because after all these are values of angular frequency. So, although I had written t1 earlier, it is better I use a more suggestive value here. And essentially this was related to a sin x by x kind of pattern. In fact, we know what that sin x by x form is. So, the sin x by x form was as follows. You see, the kappa 0 remained where it was. Then you had sin omega 1 into t minus t1 divided by t minus t1, you can keep omega 1 here and here as well. So, now we had an x0 that looked like this. So, this is x0 really, what you have here as the argument is x0. So, this is of the form 2 kappa 0 omega 1 is a constant as you know, sin x0 by x0. We can sketch this, that is not difficult to do. That would have an appearance like this from what we derived in the previous session. The only change is the height would now be 2 kappa 0 omega 1 instead of 1. And x0 here, x0 is omega 1 into t minus t1. So, it is a question of matching. And now, you see, the point is when omega 1 tends to infinity here, what is happening really? We essentially have oscillations, and these oscillations are dying down smaller and smaller. Look at them. So, essentially we are looking at omega 1 tending to infinity. So, you can see that this quantity goes to 0. So, it is interesting. What we find is that as long as you have taken a large enough value of these limits of the integral, you seem to be going towards 0. It is also a function of t minus t1. That is another interesting thing here. So, what exactly is happening here? So, if you look at the integral here, the integral is troublesome. Troublesome because the integrand has a magnitude of 1. So, you have a magnitude 1 integrand being integrated potentially over all the real axes. So, actually the integral is divergent. That is the problem. It is not really a convergent integral. So, where is this going? As a function of t minus t1, you can think of it like that. It is a function of t minus t1 and the integral is on omega. Now let us look at the integral as we evaluated. So let us look at this. So here, as omega 1 tends to infinity, this height also diverges. Where is this null? That is also important. The null occurs at omega 1 into t minus t1 is equal to pi. That means t minus t1 is equal to pi by omega 1. As you increase omega 1, what is happening to the sin x by x function? For a given t minus t1, let us look at this expression. So here x0 is always fixed, but then what is happening to the area under the main lobe? That is something that we should reason. This is diverging, this is not a function in the true sense, in the regular sense. The sin x by x function, when omega 1 tends to infinity, the height in the middle is going to infinity. So it is not a function really there. What is it then? So it is suggesting to us movement towards something that we had encountered in the first module, namely the impulse. Essentially this is going to a situation where it captures non-zero area in 0 widths. That is the central idea. So you see, the interesting thing here is that even as the height goes to infinity, the width starts reducing towards 0, and finally an asymptotic situation is reached where essentially a certain amount of area is encapsulated all around 0. So if you think of this as a function of t minus t1, see now we have to change our focus. We have to think of this as a function of t minus t1, not x0 anymore. So let us look at it as a function of t minus t1. We now think of this as a function of t minus t1, not x0 anymore. And of course everything is just proportional. After all, x0 is essentially omega 1 into t minus t1, so it is just a scaling. So on the t minus t1 scale, or on the t minus t1 axis, of course this point continues to be 0, but now the null comes at the point pi by omega 1 on both sides. So minus pi by omega 1 on this side, and of course the spacing between the nulls is also the same, spacing also pi by omega 1, and the height here is of course 2 kappa 0 times omega 1. So now let us visualize that you could start thinking of this part, essentially this part, approximate this by a triangle, approximate asymptotically by a triangle. Now if you asymptotically approximate by a triangle, you can find the area of that triangle, and you can do the same thing for the other side lobes, these side lobes here. So this side lobe, and then this side lobe, and then this side lobe, and similarly all these side lobes here, all these are smaller triangles here. And essentially what we have is that the height multiplied by the width, which is approximately 2 kappa 0 omega 1 multiplied by 2 pi divided by omega 1, starts approaching a constant for the main lobe. That is interesting, that is the important part here. So the main lobe starts having constant area, and that is also true of those smaller lobes on the sides. So you can visualize a situation where as you go towards infinity, you then have a constant area no matter how large you make omega 1. And all this area now gets concentrated around 0. What is this? It is an impulse at 0. In fact, now you have to worry about what that area is, and that is why you have the flexibility of a choice of kappa 0. The choice of kappa 0 can be such that that area can be made unity. In fact, it turns out that if we choose kappa 0 equal to 1 by 2 pi, we get this becoming a unit impulse, delta t minus t1. And then we have a very beautiful situation. We have integral minus to plus infinity ht1 times this integral inside, kappa 0 into minus to plus infinity e raised to the power j omega t minus t1 d omega, all this business, and then dt1. This whole thing has been replaced by delta t minus t1 with a choice of kappa 0 equal to 1 by 2 pi, and therefore you would get minus to plus infinity h t1 into delta t minus t1 dt1, which is simply h of t. So, there we are. What we have done here is to give a brief explanation of how this orthogonality has worked when you have gone from a finite period to the infinite omega axis. You needed to worry about what happens when these sinusoids last forever. Do they still remain orthogonal? So, the orthogonality is in the sense here of an impulse. It is a more generalized concept of orthogonality. The dot product here that you see, or that integral which you encountered as a part of the orthogonality issue, it is not very clear here exactly how this orthogonality has come, but it has come as a consequence of the reconstruction formula. We will see more about it later, but right now in the reconstruction formula you required movement towards an impulse, and that is what has happened here. If you take a rotating complex exponential all over the time axis. Well, this is a slightly difficult part of the Fourier transform. I have explained certain things informally. We will see more in the coming sessions. Thank you.